Today we will talk about hypothesis tests for two means. This is the second video in the series for hypothesis test for two population parameters. We want a hypothesis test that involves two population means, and in this context, we will work with a sample x1 through xm, which is coming from a population with mean mu1 and variance sigma 1 squared. And we will have another sample, random sample, y1, y2 up through yn, which is coming from a population with mean mu2 and variance sigma 2 squared. Furthermore, we will assume that the random samples x and y are independent of each other. When working in this setting, if the populations are normally distributed and the population variances, that is sigma 1 squared and sigma 2 squared, were known, then recall that we had used the z statistic defined as x bar minus y bar minus mu1 minus mu2 divided by the square root of sigma 1 squared over m plus sigma 2 squared over n. And we can use this statistic to set up a hypothesis test where the null hypothesis is that the difference between the means equals the null value delta 0, and we have three possible options for our alternative hypothesis: the lower tail test, the upper tail test, and the two-tailed test, or the two-tailed alternative hypothesis. In this setting, we know that the test statistic z has the standard normal distribution, and we can use this distribution to calculate the p-value, where the p-value is going to be phi of z. If we are working with the lower tail test, it's 1 minus pz. If we are working with the upper tail test, and it's 2 times 1 minus phi of the absolute value of z if we are working with the two-tailed test. And note that z here is the value of the test statistic evaluated on the sample data. We would now want to relax some of the conditions here. So what if we did not know what the population variances were, or what if the population was not normally distributed and the population variances sigma 1 squared and sigma 2 were also not known? We have two settings here, the first one being the two-sample t-test. The assumptions for this test are that our samples, x1 through xm, are going to come from a normal distribution with mean mu 1 and variance sigma 1 squared. And the sample y1, y2 up through yn is going to come from a normal distribution with mean mu2 and variance sigma 2 squared. Furthermore, we will assume that we don't know what the population variances are, and we will also assume that the sample sizes n and m are small. In this setting, we define the sample variances s1 squared and s2 squared as follows. These are sample variances for the two samples, x and y. And we can consider the test statistic, t, defined by x bar minus y bar minus mu1 minus mu2 divided by the square root of s1 squared over m plus s2 squared over n. This statistic has approximately the t distribution, and the degrees of freedom of this distribution has kind of a complicated formula that involves calculating the sample variances on the sample data. So it is written in terms of the standard errors, SC1 and SC2. It's the quotient of SC1 squared plus SC2 squared divided by SC1 to the 4 divided by m minus 1 plus SC2 to the power 4 divided by n minus 1. And this number needs to be rounded to the nearest integer. Notice that the calculations of the two standard errors, SE1 and SE2, depends on working with the sample data, that is x1 through xm and small y1 through small yn, respectively. Uh, we will now describe the two sample t-test procedure. The null hypothesis is that the difference of the means equals the null value delta 0. The test statistic is calculated as small x bar minus y bar minus delta 0 divided by the square root of s1 squared over m plus s2 squared over n. The p-value calculation will require us to work with the t-distribution with new degrees of freedom. The value of nu has been calculated earlier using the two standard errors, SE1 and SE2. The p-value calculation will of course depend on what the alternative hypothesis is. So in the lower tail test, we are going to look at the area to the left of the test statistic t under the t-distribution with new degrees of freedom. For the upper tail test, we are going to look at the area on the right of the test statistic t. That's the value for p under the t-distribution. And for the two-tailed test, we will be the value of p is going to be 2 times the area to the right of absolute value of t under the t-distribution with no degrees of freedom. To get the test result, we will compare the p-value to the significance level. If the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is bigger than alpha, we fail to reject the null hypothesis. Note that to use the t-test, there are two important assumptions or observations that we need to make with regards to the population being normally distributed and requiring that the two random samples are independent of each other. We next move on to hypothesis tests for two means when we might not have information about the distribution of the population. That is, we don't know if the population is normally distributed. And we will also assume that we do not have any information about the population variances sigma 1 squared and sigma 2 squared. In this setting, if the sample sizes n and m are large, we can consider the statistic z equals x bar minus y bar minus mu1 minus mu2 divided by the square root of s1 squared over m plus s2 squared over n. And this statistic approximately has the standard normal distribution. We can use the sample data to calculate the value of small z, that is going to be small x bar minus small y bar minus delta 0 divided by the square root of s1 squared over m plus s2 squared over n. Now using small z and noting that capital Z had the standard normal distribution, we can calculate the p-value as phi z if we are working with the lower tail test, 1 minus phi z if the alternative hypothesis is corresponding to an upper tail test, and 2 times 1 minus phi of absolute value of z if you are working with a two-tailed test. Note that phi in this case is the cumulative distribution function for the standard normal distribution, and the test decision in this case would be arrived at by comparing the p-value to the significance level alpha. We need to note that because m and n are large, we don't need the normality assumption on the population distribution. And also, even if the population variances were not known, we can use the sample variances to approximate them and still get a standard normal distribution for our test statistic. Also note that when working with large samples, we are more likely to reject the null hypothesis, which can lead to interesting discussions about what's the relevance of the statistical significance versus the practical significance of your test. To summarize, we have worked with hypothesis tests for two means. When the population variances were not known, we had the t-test and the large sample z-test. This is all for now. Take care of yourselves, and I will see you around.